Okay. So on Monday we finished bi-connectedness testing using DFS, single DFS. Right. So this is the pseudocode. This is the Hopcroft-Tarjan algorithm to find all articulation points in a graph, in a connected undirected graph. Any questions about this? And then we completely changed the topic to heaps. Right. So we'll now do for several weeks we'll do different kinds of tree-based data structures. The ones we have seen are BST, red-black tree, and now heap. So heap is it is again drawn as a tree, but it is weaker than BST. So it may not be balanced, and it may not even have the children in order. Okay, so left child may be bigger than the parent, although still some sanity is needed. So the sanity property here is that parent has to be the minimum of the children. So like 4 is the parent, so the children are 7, 11, 5. Okay, they cannot be 4 or less than 4. Is the smallest key. So what we want to implement in this DS, what we want is we want the minimum in the heap, which is the root, and we want to update the heap so that the minimum is deleted. So that is the delete min, extract min operation. Then there is a decrease key operation, which is basically you can pick any node and completely change it. But it is written via decrease delta. Okay, so node P's value or key is decreased by delta, which will destroy the heap property. So you have to again change the whole heap. Okay, we'll see an algorithm for this. And merge is 2 heaps are there, you merge them and make a single heap. Okay, so these are the operations needed. And we will implement them staying close to an array, because the goal of heap is to reduce some of these log n further to constant O1, big O of 1. So we'll try to use the properties of both binary tree and an array. So that will be a completely new implementation. So let us see some, any questions till now? So then let us see some basic properties which help us in maintaining the array. So labels in a tree, we'll use now labels, which is where exactly a node is present. We'll think of it as an array. So what it means is the following. So this is, these are the levels. So this is level 1, then level 2, level 3, level 4, and so on. Okay, and these numbers are not the keys, but these are the labels, which is if this tree was stored in an array, then this is where it will be stored. Okay, so the root will be stored at 0, left child at 1, right child at 2, and then pushing forward. Okay, so children of 1 will be after 2, and then children of 2 will be after 1 is over. I mean, after once children 3 and 4 are over, then you will put 5, 6, and then you will put children of 3. So this is the way we think of the array implementation. Also, we want this tree to be as close as possible to a complete binary tree. So what does that mean? What is a complete binary tree? I don't think we defined this. Right. Yeah. So that is somewhat the definition of complete binary tree. I mean, it may just mean that in level L, so let's say we use L for the level. So, and then we need a property. What is the number of elements in a level? Or maybe easier will be number of nodes up to level less than equal to L. What is that number? So since this is a binary tree, labels in a binary tree, since it's a binary tree, so up to level L, you should have around 2 raised to L nodes, right? You cannot have more, which I think is satisfied. Yes, up to, it is 2 raised to L minus 1. Okay, you can check the formula. So L equal to 1 gives you 1, then L equal to 2 gives you 3, and it gives you then 7 and so on. Right? So this is the exact number. So if you had a full binary tree complete, then let me call that full. So if you had a full binary tree of level L, then you will have exactly 2 raised to L minus 1 nodes. And how many in a single level? At level L. So then you subtract, right? So you get, yeah, L minus 1 above in the superscript. So in a level, you have these many nodes in a binary tree. Okay, but you may have fewer. So complete binary tree, whenever you see this phrase in this course, it will just mean that if your tree has L levels, then up to L minus 1 it is full. Okay, it is maximum, achieving the maximum number of nodes. At level L, it may not achieve the maximum, but then everything has to be present on the left side. Okay, this is what complete binary tree means for us. So complete binary tree of L levels has all the nodes up to L minus 1 levels. Well, all as in max possible. Has max number of nodes possible up to L minus 1 levels, and L level, at the L level, Lth level is filled in the left side. Okay, so this is what is happening. So at level, so this is a level 4 complete binary tree, because up to 3 it is maximum. And at level 4, some things may be missing, but whatever is present, it is filled from the left side. Okay, so 7, 8, and then 9 onwards, everything may be missing. So in particular, what is not allowed is something like this. Okay, so this is not a complete binary tree in this course, because if you want to have a fourth element, this 3, then it should be present where? Should be a left child of 1. Okay, so we want the array to be defining a unique tree structure, which we are calling complete binary tree. So now there is a one-to-one correspondence between array and complete binary tree. Okay, you can go back and forth. Okay, so this is one-to-one. So given an array, there is a unique complete binary tree, and given a complete binary tree, you have the array. So for the array, you have to organize 0 to n minus 1 labels like above. Okay, giving starting always from the left. Is this clear? So that is the setting, and then we will go much deeper now. We'll actually write down all the formulas about parent and children, looking at an array location I, looking at the location I. So based on that, we have the following properties. So first is leftmost node at level L is what is the label on the leftmost node at level L? What do you read? 2 raised to L and then minus 1 down. Okay. So you can check that. At level 2, it should be 3. So you will see 3 on the leftmost side. So this just follows from the count that we have put, number of nodes up to level L. From that count, it follows. Okay, so now kth node from the left at level L is what? So k equal to 1 is above, that is, the answer is 2 raised to L minus 1. Then what is k equal to 2? What comes after left? Right, so that is just, you just add k minus 1 to this, so you will get 2 raised to L plus k minus 2. Okay, so at level L, you know that, so this is basically giving you the way to read an array as a tree, visualize a tree on the array. Right, so array is a linear representation, but you can make it two-dimensional by these formulas. So when you go to the index 2 raised to L plus k minus 2, then you will know that in the tree you should draw at level L kth location, kth node. So let us call this node for the following formulas. This is the node V. And this number, let us call that J. Okay, we'll reuse this in the subsequent formulas. So now, what is left of V? Left child of V. That is harder. Sorry? In the superscript? What? Is that a mistake? At level 2 you are getting, yeah. So another L minus 1. This one. Yeah, somehow I don't like that. We can start from level 0. Yeah, actually we should have done that. So then these formulas, are they correct? Nodes up to level L minus 1. So for L it will be L plus 1. And this will just be L. Okay. Yeah, this looks better. So so at level L, leftmost has label 2 raised to L minus 1, because for L equal to 0, you wanted answer 0. Yeah, so that matches. Then kth onwards, it's fine. So let's now look at the left child of V, of this one, this node V, numbered J. So what is that? Yeah, so it is 2J plus 1. Do you see this? This is, with J, this is easy to verify. You can just manually verify that left child of 2 is 5. So it is 2 times 2 plus 1. Right, and that formula holds true everywhere. So 2J plus 1, then you can expand it to more complicated one, which is 2 raised to L plus 1 plus 2K minus 3. Okay, so the left child of the kth node from the left at level L. Okay, it is this one. That's the expression. So in the array, again you can move to the left child, okay, by jumping from J to this place, 2J plus 1. What is the right child? Yeah, that is now easy. And what is the parent? In the array, if you want to move to the parent of V, where should you go? Roughly J by 2, right? So, and exactly you can write J minus 1 by 2. So this also you can just check empirically. When you are at 6, you want the parent, so you just halve. And when you are at 5, you halve. Okay, so both the parents are 2, and so on. Is that clear? Okay, so then this is now a complete description of when you have array implementation. How will you, if you wanted a pictorial tree, then this is how you can draw it. Right? You can exactly know who is the parent and who are the children when you are at jth location of the array. Okay, so these formulas will be useful for the pseudocode. When you write the pseudocode, then you will have to exactly implement these formulas. To see array as a tree. Okay, so from array you can go to tree and vice versa by these formulas. You just have to hard code them in the pseudocode. But remember that this is not any tree but the complete binary tree representation. Okay, otherwise the formulas will all be lost. So we will see heap as this. Okay, so heap will be this complete binary tree with now instead of the labels will be in the background. At the nodes you will have keys stored, and with the key or the record there is also this underlying array label, which we have seen here in the formulas, and additional axiom of parent less than the children in terms of key. So your heap will be like this. So now you have these keys. And which translates to the heap as an array instead of heap as a tree. So how do you express this? What is the first element? What is H0? Oh, you are already confused. H0 is the root, right? So that is 4. After that, yeah, so 14 and 9, and then 17, 23, and 21. So this is 0, 1, 2, 3, 4, 5. Yeah, so there were 6 elements in the heap, so 0 to 5 is the array indices. So the red ones are the labels or array indices, and these are the keys. Okay, we'll need both. And the keys, because of the labels, can also be organized and seen as a heap. So you can go back and forth. And you can see that the heap axiom is satisfied at every node. Okay. So, and n here is 6. So each is an array storing a heap, and n will be the size of the heap. So in the implementation, you have to maintain a arbitrary length or unknown length array, and together with that, you have to also store a variable n, which tells you the length of the array, which tells you the size of the heap. Okay, so that you know that you only have to worry from 0 to n minus 1, and not beyond. So h is a dynamically allocated array, and n is the length that you want to work with in this heap. Okay, these are the two things you need for implementing a heap as an array. And the min of h is, as an array. When you are given heap as an array, then minimum is just h0. Okay, that's the basic heap axiom. So that is done, right? You needed query operation was min h. So in the array implement, that is simple, that you just have to read the 0th element. So next is extract min. What do you do there? Okay, so this is far more complicated, because here you have to shorten the array. You have to actually delete 0th element, so 4 gets deleted, and then everything changes, because it isn't a tree anymore, it is not a heap. So you have to form a new tree, maintain the heap axiom. So we want to write the pseudocode for that, right? So let us see that pseudocode through an example. So what should you do in that picture, right? So we'll just implement the pseudocode pictorially on this heap tree. So we want to delete 4. So from red-black tree deletion, you should do what first? Somehow you should send that to the leaf, right? Swap with a leaf. And then delete the leaf, and then after that make it a heap. Yeah, but those things, see, this is that it doesn't have BST axiom, it's just a heap. So if you want to find second min, where can it be? Sorry? H1 or H2? Is that right? Yeah, that follows from the axiom. So you can swap with that second min, but then what? Then you have to delete that location, so it will still be, you still have to go deeper. So we'll do that in one step, that swap. So let us do the following. So let me keep the graph structure at least. And swap 4 with 21. So I am swapping just the 0th element, the first element of the array with the last. That is the first step. Okay, this will be helpful for some reason. At least in the array, it is easy to do. In constant time, you just swap first with the last, because now you can delete the last. Okay, so you swap h0 with hn minus 1, so 21 is replaced by 4, and 21 goes above, and then you delete. So when you delete, then you see this is the leftover. Right, so the heap or the array has become now, n has reduced by 1. Right, 6 has become 5 now, n equal to 5. But what is the problem? The problem is that the heap axiom is violated already at the root, right? Because 21 is not smaller than the children. So for that, what should you do? So for that, you pick the min child and swap with that. Yes, very good. That is what you will do. This will now cascade down. Wherever there is a problem, it basically means that that parent is, that node has a child with smaller value. So you should just swap with that and cascade down. So the time will be how much? The height, right? So the time, as we have seen with BST and red black tree, it will just depend on the height of the tree. And the height you can see is how much? Yeah, that comes from this formula. This 2 raised to L minus 1 formula, or 2 raised to L formula. So that is around n. So the levels are only log. Okay, so this is what you will be using. So up to level, so for a level L tree, this value has to be smaller than n at all times, which means that the level can never exceed log n. Okay, so that is the number of levels or the height. So what we are doing will give you a pseudocode which is not bad. Extract min will take only log n time. So let's finish that. So 21 with min child, which is 9. And you had 14, 17, 23. Okay, so, and is this a heap now? So now it is fine because 14 is bigger than 9. So that part you don't have to correct. And once you come down to 21, there is no child. So there also you have heap property. So this stopped immediately. But if there was a problem, then you would have gone. You would have moved in the direction where there is a problem, which means that the problem could have been here that 9 has children which are smaller than 21. So when you exchange 9 and 21, then you should go down and handle that part of the subtree. Okay, and so on. So this cascades down, but is bounded still by the height. So this idea following the min child will take time because remember the min child is unique, right? So you will go down only in one way. In every step, you just go down in a unique direction. And then when you reach the leaf, could there be any other problem somewhere else in the tree? Yeah, so you have to check that when you reach the leaf, then all the other parts of the tree are fine. And you are at the leaf, so which means that the whole tree is fine. So you have a heap now. So overall this takes time only height of h, which is because of the complete binary tree translation is log n. So you should check this. So check the details of this as an exercise. But all the major hints are given here. Okay. Any questions about this? So next we need to implement is insertion. So now we want to extract min is done. Now we want to insert. So basically this is one of the most important operations, update operations. This is how you grow the heap. You want to insert x somewhere. Let us say you want to insert in this heap x equal to 3. And the heap was this 4, 1723 and 921. Okay, so that was the heap. You want to insert x equal to 3. What should you do? So first step should be kept very simple, like we did before. So insert 3 just at the end of the array. Right, because the first thing you want is the complete binary tree picture. So which is why it is important that you don't try to act too smart and just add 3 here in the end. So this violates the heap axiom, but still at least the picture is, the complete binary tree picture is correct. Okay, so you have the correct mapping now from array size to the tree and all the formulas. So that is the first step. What you do is add at the end of the array. And increment n. Okay, so with the new n, you have all the formulas continue. What are the children? What is the parent? So you have this tree now in mind. In the pseudocode gives you formulas to get to this picture. And now is the time to correct. Next step will be correction of heap axiom, right? What do you do here? Yeah, since the parent is larger or the child is smaller, so you do the same thing that you did with this extract min, right? It's the same idea. So again, 9 sees that 3 is smaller, so 9 should go down. Will be swapped with 3. So again swap with the min child, which is unique. and 1723. So that is the part we will be swapping these 3 and 9. So we are now, the control is at that stage. So the subtree heap property is now correct. We have forced that. But now what will happen? Now the problem will shift above. Right? So now you see that parent of 3 sees a smaller child. So what should you do now? Yeah, so again, I mean, you have some, obviously you have this starting point. You know that everything is right, is correct on the left subtree of the root. Right? The problems are only happening on the right subtree of the root. So this 4, 14, 17, 23 always stays fine. I mean, till now stays fine. So you know that the only thing to exchange is these two. So again the same idea, swap with the min child. So you have 3, 4 comes here, 14. These are the keys, not the labels, remember. Okay, so now you can check, since you have reached the root and you have corrected the right subtree, left subtree was already fine, so now you stop. Right, so this is a heap now. Is that clear? Okay, and what operation do you want? From upward, so that was happening in extract min. No, you have formula everywhere. For every j there is a formula. For every j, any location where you are, let's say j, you know the children and the parent and the, if you want ancestors also. Everything is known. So which is why it is correct to draw these pictures, because the pseudocode knows about these pictures from the array. We are swapping with the parent. Every step is that, right? This swap with min child means that parent and child are swapped.
So in a particular step you are checking that a particular node value is lesser than or equal to its parent instead of checking the parent value is greater than.
But what is the difference? It's the same thing. It's the same inequality you are checking. No. There is no single pointer. The control is always at the red place. Because the red place is what you have changed right now. So the error will be in this vicinity. And how to move around in the vicinity is given by the formulas. So the pointers are given by the red colors, like the 21 and 4 were interesting there. Then 21 was interesting. Then from 21 you went to 9, which is now done. And similarly here in insert, 3 is where the pointer is, and 3, and then 3 goes to the top. So and all these things you can actually work out the formulas from the array where you are at. Yeah, so that is part of the detailed proof. So since we know all the formulas, So although the data structure you are given, physically what there is on the computer is just an array, but because of the formulas you can move as if you are moving in a tree. Right, which is why we wrote down all the formulas. So you just have to copy paste them in your pseudocode. So you know how to move in the array like a tree. We can do this in height. So insertion takes, again, height of h multiplied by constant time. Okay, so the number of times you are swapping with min child, that number of times is given by the height. And just swapping with the min child can be done in constant time, because that is only calculating the where to go from j in the array. In the array, going from j to 2j plus 1 is a constant time operation. Right, so that is the big O of 1. So this again is big O of height. Which is less than equal to log n. Okay, so we have done both extract min, which is like deletion, and insertion in log n time. Maintaining the heap structure. So next will be this decrease key operation. So decrease key is just go to pth node and arbitrarily change it, which is given by this decrement delta. How will you do this? This is actually exactly similar to insertion. Right, you are, let's say you change 23 to 20. Yeah, I think that is, no, but the deletion algorithm I have not given you. How will you delete? That was just extract min. That is not general deletion, because if you delete 23, then it stops being a complete binary tree and then the array mapping is gone. So we cannot change the picture. We can only change the values. So 23, suppose you want this decrease key, you want it to be reduced to 20, or let's say drastically you want to reduce to 13. So if 23 decreased by 10 you want to do, it becomes 13, and then the problem will be with its parent. So again you will move up like you moved up in insertion. Okay, so this is exactly like insertion. So it's a sequence of swaps. Which is parent to the min child. Okay, so you are just swapping, and these many times, each swap takes constant time. So this is also log n. Okay, so we have done all the promised update operations, except this one, the last one that we have to do next time is merging two heaps. Okay, this will be the most interesting. Most complicated will be merging two heaps. because we don't want to spend the trivial time, but something faster. So we'll discuss this in the next class.